Hello guys, welcome again to another video. In this video we are going to solve and continue our problems from integration which we started in the previous video, and we shall start with the problems that I would show you right now. So the plan is I will write down a problem of integration, obviously of indefinite integration, and I'll give you like 5 to 10 seconds for you to solve it, and then you can proceed to watch the video where I will be solving it, explaining all the necessary techniques what we have learned. So all of these problems will also have what we have learned in the previous sections, like integration by parts, method of substitution. So those things will not be a surprise to you, but obviously the way they will be used might be a little different, because every problem has its own unique flavor, but some of the problems might also be the same. So let us begin. So problem 1. So problem 1 is integral of tan of theta divided by cos square theta. Now tan theta by cos square theta's integration, this can be achieved, but we just have to use a few properties first. So remember that tan theta, notice that so tan theta is equal to sin theta by cos theta, right? But why do we need it? Because observe that there is a cos square theta in the denominator, and if we were able to find out sin theta by cos theta as tan theta, then what will happen is there will be a sin theta in the numerator and only cos theta or some expression of cos theta in the denominator, right? And sin theta is the derivative of cos theta is basically minus sin theta, and the derivative of sin theta is cos theta. So in both ways we can do is we can achieve a value which is more suitable. That is, what we can do is as follows: I equals to right. Now we can make the following substitution. The substitution being u equals to cos theta, because this will give us du equals to minus sin theta d theta. Putting it in the integral, we have I equals to so sin theta d theta would just be minus of du, as you can see from this line, and the denominator would just be u cube, right? Now this would mean that this is minus du into u to the power minus 3. Applying the rule, we get u to the power minus 3 plus 1 by minus 3 plus 1 plus c, or this is minus u to the power minus 2 by minus 2 plus c. So the minuses cancel off, and what you get is 1 by 2 u square plus c. And if you put the value of u, it becomes 1 by 2 cos square theta plus c, which is the answer to our integral. So I hope this was solved by most of you, considering the fact that it can be solved in multiple ways. One of the other ways could be to use cos square theta into cos theta, and so in the tan theta by cos square theta thing, what we can use is we can multiply by sec theta above and below and find out that the derivative of sec theta is just sec theta tan theta. So that is another way to do it. Okay, so let's move on to the next problem. evaluate integral of x into tan x dx. So I'll give you 5 to 10 seconds for to think about and solve this integral, or have a clear mind map of what to do in this kind of integral. Right, so let us begin. We know that given this kind of an integral where it's a product of two different kind of functions, where x is an algebraic one and tan x is a trigonometric one, we can write that I equals to integral of x tan x dx, right? And we can notice that x is an algebraic function and tan x is a trigonometric function. To clarify, I'll just write it down here. X is algebraic and tan x is trigonometric. So according to the Eilert rule, according to Eilert rule, we have first function then should be since you can see that a comes first before t, so what we can do is first function would be x and second function should be tan x, right? And applying IBP, we have I equals to x into integral of tan x dx minus, so this is one way, and then again we have x into the differentiation of x, which is like x prime into integral of tan x dx, right? So integral of tan x is basically log of sec x, so it is x into log of sec x minus this is 1 into log of sec x dx, right? Now log of sec x can also be evaluated, but this is a different kind of a problem, because as you know that the first part here is, according to the IBP rule, is x into log of sec x, right? And the second part becomes something like 1 into log of sec x into dx, right? So since there are two different kinds of functions, and this log of sec x part here is something that we cannot evaluate using elementary functions, but we can rather do it using an infinite series, right? So that is one way to do it, because integral series are some of the best ways to solve problems. So log of sec x can be evaluated by noting the fact that log of 1 plus x is equal to summation n equals to 1 to infinity minus 1 whole to the power n minus 1 x to the power n by n, right? And we can note that log of sec x is equals to half of log of sec square x, but log of sec square x is just log of 1 plus tan square x, and we can apply this formula here to find out the resulting answer. So this is an example of an integrand which cannot be evaluated in terms of elementary functions, and it can never be, which can be proved, because this is equals to just x into log of sec x minus this integral, and this integral does not have any representation in elementary functions. So just to give an example, if you were encountering some of the integrals like this is how you should be dealing it with, right? Okay, but to quote an example, let us find out another integral. Let us find another one of the similar type. So this one is x into tan square x dx, right? So again, set first function as x, second function as tan square x, then I equals to x into tan square x dx, and applying IBP, what we do get is this: x into integral of tan square x dx minus d dx of x into integral of tan square x dx. So what is integral of tan square x dx? So to make things simpler, let us say b is equals to integral of tan square x dx, and we can evaluate b separately and then put back the value. So this value would be equal to, we know that tan square x is basically sec square x minus 1 dx. We can separate the integrals like this: sec square x dx minus 1 dx, and that integral of sec square x is just tan x, because the derivative of tan x is sec square x. So tan x minus x plus c, right? So we omit the c part when we are using it in the second integral and the first integral, because we are going to just put a c outside. So therefore I is equal to x into tan x minus x minus integral of tan x minus x dx, right? So this becomes x tan x minus x square minus integral of tan x plus integral of x dx and tan x dx. This would give us x tan x minus x square. So the integral of tan x, as we have found previously, is log of sec x. So this is log of sec x, and this would be x square by 2, and then there would be a plus c. So this is the answer. So we can see that the integral x into tan x was not really evaluated in terms of elementary functions, whereas the integral x into tan square x could be evaluated. So a minor change in an integral could result it in being not solved using elementary functions. That is how complex the integrals tend to be. And once we get to know about the definite integrals, you can see that we can this definite integrals only mean that they are area under the region of a curve. So they always have a numerical value, but that does not mean that the numerical value can always be expressed as in terms of elementary functions. For example, the function sin x upon x, cannot be integrated, as it does not really have a elementary antiderivative, but the definite integral can be. So the definite integral of sin x by x can be evaluated, and it is equal to 0 to infinity sin x upon x dx is just equals to pi by 2, and it's a result. But whereas the indefinite integration of sin x by x without any limits cannot be evaluated in terms of elementary functions, it can only be evaluated in terms of a series. So we understand here that this kind of integrations do not really pave our way, and there is no other way to understand if an integral has an antiderivative or not. But a definite integral of the same thing which does not have an antiderivative in its indefinite terms may have a result even in terms of elementary functions, and definitely has a result in terms of numerical answers. So that is the difference between the two. So again, in the next video we shall start doing about another problems, and for now let us end about this. So thank you for watching the video, and please do check in the link in the description about the Breatter Maths app, where all these video lections and all the notes and theory and everything else is provided, so do check it out. Thank you.